Hello everyone. In this video, we will continue to discuss topic 5.3 electric cells, and in particular, we will continue to discuss discharge of cells. All right, so we introduced the idea that cells have a certain capacity, and they sort of, given that capacity, can sustain a current for a time, which can be read off the capacity directly. But the idea is that as cells discharge, their EMF and terminal potential difference, in which case we mean terminal potential difference, but often people will just discuss the EMF. But the terminal potential difference changes, largely due to an effectively increasing internal resistance. So remember that I discussed when we hit internal resistance that we were modeling the internal resistance as being constant. This is one of the ways in which it's not. As a result of that increasing internal resistance, you actually get a very distinct what's known as discharge curve for most chemicals. And a discharge curve looks something like this. There's almost always a particularly quoted EMF that is equal to the average terminal potential difference for most of the lifetime of the battery. However, you will also see that right at the beginning of any particular use of a cell or battery, there's an initial drop-off. And what's happening there is sort of the low-hanging fruit of the charge has been reacted, and some of those chemicals are now slightly in the way, and so you get an initial drop-off right here. It then stays pretty constant for a while, okay? And then right near the end of its lifetime, that is near the end of its capacity, the terminal potential difference drops off precipitously as the internal resistance increases. And that happens because the discharge chemicals almost always are basically just getting in the way of the other chemicals. And there's right near the end of its lifetime, it falls off pretty precipitously. Notice that this discharge curve will look different for different steady currents. So this is an example of 3 discharge curves for the same initial terminal potential difference and capacity, but with different currents. Notice that if you run the same battery down using a 0.5 amp current, that is roughly twice as long. It has roughly twice the discharge time as a 1 amp current, okay? Yeah. And you can also see that a lot of the currents here, so the actual terminal potential difference for both red and green are slightly higher than for blue, as the impact of that internal resistance is just a little more felt if you're trying to move charge along a little faster. Notice that as secondary cells are charged and recharged, they do, as you know, eventually lose capacity over time and recharge cycles. And most good batteries, good sort of rechargeable batteries of the kind in your phone or computer, it really does depend. But they'll have some total number of expected cycles where they will operate at reasonable capacity, somewhere between 2,000 and 10,000. It really does depend on the device and the particular cell. So that's what this is. So in general, you should be aware of the general shape of the discharge curve, its relationship to the total capacity, and particularly these fall-offs right at the beginning, at the end, in the terminal potential difference of the cell in its lifetime.